This video we're going to talk about some special subsets of the power set of A. So what we should do first is a little bit of review in case you have no idea what I'm talking about with the power set of a set. So here's the definition. If A is a set, then the power set of A is the set of all subsets of A. So again, power set's always a little bit weird at first. It's a set of sets, so it's all possible subsets of A. And what we're going to denote the power set by is this fancy P of A. So it's kind of like a function notation kind of thing. Okay, and so if you have no familiarity with power set at all, you could go and watch the other video that I made, or any other video or book that has information about the power set in it. What I care about are what are some things that mathematicians tend to do with the power set? And mathematicians like to study subset of the power set that satisfy certain conditions. And what I'm just going to talk about in this video are just two such examples. Of course, there are tons and tons more. So let's just look at two examples that try to illustrate what I mean. What are certain subsets of the power set that satisfy some conditions? All right, so the first example that we've got here, let's let fancy T be a subset of the power set of A. So fancy T is just like a bunch of subsets of A. And I'm not saying we pick all of them. I'm saying we're going to reach in, we're going to pick some. But here's what I'm going to stipulate, that the handful of subsets that I picked out of the power set, that they all need to satisfy. And of course, when I say handful, I don't mean to imply that there's like finitely many. Maybe there's a ton. Okay, so T should be, again, a bunch of subsets of A that satisfy the following conditions. So here are some conditions together that mathematicians have deemed important for certain applications. So the first condition here that we've got is that the empty set should be in T, and the whole set A should be in T. The second condition that we want to have happen is that if AI is in the power set of A, for each I equals 1, 2, and maybe there's infinitely many of them, but countably infinitely many of them, and if each of the A's is in T, which is a little bit redundant, I just wanted to make sure that we all understand that the AI's are subsets of A, and if each of the AI's are in T, then when I take their union, that should be in T as well. So the union of stuff in T, no matter how many you had, even if you had an infinite amount of them, a countably infinite amount, that should be in T as well. And the third thing, if you took two things out of T, A1 and A2. So I've kind of bypassed reminding you that A1 is really in the power set and A2 is in the power set, just so we're comfortable with where they come from. What I care about though, if both of them come from T, then their intersection, that set has to be in T as well. So another way to kind of say number two is that the set T should be sort of like closed under countable unions. And another way to say number three is that T should be closed with respect to intersections of finitely many elements at a time. So there's nothing special necessarily about taking two elements at a time, like A1 and A2. But the point is, though, it doesn't necessarily work if you take an infinite number of elements here. So if you took 1,000,000, that's cool. But if we try to say an infinite amount, like a number 2, intersection doesn't work that way. Anyway, though, I'm kind of harping on this a little bit too much. What if you had a collection of subsets that satisfy these three properties? They get a name, and we're going to call that set T a topology on A. So why is this useful? And so what those three properties end up allowing me to do is they allow me to extend notions that I've seen in like a calculus class about continuity. They allow me to extend that past Euclidean space. And maybe you've taken multiple calculus classes and you know that there's a continuity in 1 dimension and there's continuity in 2 dimensions and 3 dimensions. But anyway, in like your calc classes, you're probably just sticking around Euclidean space. So what we're going to do is we're going to generalize that idea to any set, even if it's not Euclidean space like we're used to. And the other thing that's kind of mind-blowing about it is when you see continuity, for instance, in the context of a calculus class, it's very dependent on the ability to measure distances between 2 points. What topologies allow us to do, though, is they allow us to talk about continuity in a way that's really independent of distances. So I do not need a way to measure distances between 2 points and talk about this concept of continuity. Pretty wild, pretty cool. So if you're interested in that, again, the point of this video right here is just to show you that what if I reach into the power set of A and I pick out a collection of them that satisfy these three properties, that gets a name, it gets a topology, and they're just trying to say a teeny tiny little bit about why it's important later on and what people end up studying. Now, the second example that I want to do, Number 2 here, I didn't number it, did I? So just example 2, you trust me, I'm trustworthy. All right, so let's let fancy O be a subset of the power set of A. So again, fancy O is just some collection of subsets of A. And let's say fancy O satisfies the following conditions. So this one looks pretty similar. The empty set should be an O, and the whole set should be an O. So again, like the whole set is the A that I'm considering. And number 2, if B is a subset of A, so that's all I'm saying with B is in the power set of A. What I really care about, though, is if you picked B that's in this set O, then its complement better be an O as well. So anybody who is an O, its complement better be in there too. So that's number 2. And the third thing is similar to what we had for a topology above. If you had, say, some countably infinite collection, or I should say countable or countably infinite, I guess when I say countable, I mean, maybe it's like a finite set or countably infinite. So if you took these A's, A1, A2, A3, on and on, if each of those is a subset of A, and in particular, if each of those was in the O that we're playing with here, then the union of those A's better be an O as well. So that same idea that like this set O, this collection of subsets O, it better be closed under countable unions as well. So these are going to be my 3 sort of axioms in yellow, or conditions is the word that I used. In this case, this O gets a special name. O is referred to as a sigma algebra on A. So it's kind of similar to like how we constructed what a topology was or defined it, but it's a little bit different in some sense, in which case I don't say anything really about intersections, but I do stipulate something about having complements. All right, so let's talk about, okay, it's got a fancy name like sigma algebra, which sounds like it's important, but why is it important perhaps? And so one of the things why sigma algebras are useful, or one use for them I should say, is for trying to define ways to measure sets. And by measure, I mean length or area or volume, or just kind of generalized volume. So like, if you had a set that was like, a 100-dimensional, say, 100 is kind of a small number, but anyway, like what's volume mean in that context? I think of volume as 3D, and so we try to generalize this notion of what volume is in this way. So I'm saying measure is going to be the word that you're going to think about like generalized volume. Okay, and so one such measure is very important and popular and famous. It's called the Lebesgue measure. And I'm not going to tell you about the specifics of what the Lebesgue measure actually is and how it's defined, but I'll just try to give you a little example about like what did mathematicians, try to do with it. So for example, what if we wanted to measure subsets of the real line, so of the real numbers R? And again, I want you to think about like the real line in your head. Then like a real interval like from A to B with closed, with its endpoints, say, intuitively maybe that has measure B minus A. Whatever measure means, I bet the measure of that's probably B minus A if I'm going to define it in an intuitive way. It's like the length of that interval. But if I try to take that same logic where I'm just kind of thinking about like, I just think about how long that interval is. If I try to apply that same logic, it's pretty hopeless for when I want to try to measure the rational numbers, right, which are not an interval. And so I cannot use that logic at all. And so what this construction using sigma algebras to define this thing called the Lebesgue measure does is it allows us to measure sets like the rational numbers as well as easily measure something like the interval from A to B. So it allows me to do kind of both of those two things consistently, which is pretty cool. And so if you're curious about what's the Lebesgue measure of the rational numbers, I'm not going to tell you. You should go look it up. I'm just kidding. I'll tell you. It's 0.